Salam and welcome everyone. So today we're going to be working on the question on the screen, which says use the data from the resource section of the textbook to determine the standard reaction entropy at 298 Kelvin of the following reaction. So I apologize. Let me quickly write to determine here. I don't know what happened. Anyways, use the data from the resource section of the textbook to determine the standard reaction entropy at 298 Kelvin of the following reactions. The first reaction and then the second reaction. I wanted to mention that the textbook I'm using is the Physical Chemistry Atkins 11th edition textbook, and the question stops at the second reaction. But because I'm going to be doing this video and I want to make sure everyone is on the same pace, for example, if you don't have the Atkins Physical Chemistry 11th edition textbook, the resource section is at the back of the textbook, and I have gone to the resource section and I've written all of the values that we're going to be using. So I would advise you, or I'll actually require you to pause this video and write all of this information down so that when we start to use these values in our calculation, you're not left confused. So basically, pause this video, write all of this information down because I'm not going to be going back and forth through the pages because I actually have my own personal note. So now that you've already written that down, the first thing you have to do is whenever you're asked to determine the standard reaction entropy, the formula for determining the standard reaction entropy is just simply the summation, okay, of the molar entropy for the products, okay, minus the summation for the molar entropy of the reactants. So this is how you basically determine it. And this formula can be applied to any of the different chemical equation. So let's start with the first question. We're told that zinc solid plus Cu2 plus aqueous would give you zinc 2 plus aqueous, okay, plus Cu solid. Now, from this, we can apply what we know from what I've said. Now, the standard reaction entropy is just going to be simply the molar entropy of the products. So the first product in this reaction is Zn2 plus. So molar entropy of Zn2 plus aqueous, okay, plus the molar entropy, because of there's a summation here. So we're going to do the second one of the second product, which is just Cu solid, okay, minus the molar entropy of the first reactant, which is Zn solid, okay, plus the molar entropy of the second reactant, which is Cu2 plus aqueous. So yeah, that's basically how it's done. So now remember what I said. We are going to be using the values I'd given you. Like these values I told you guys to pause and write out is what we're going to be using. I have my book, so I'm just going to be simply substituting. So we have the value for the first one. The molar entropy for Zn2 plus is just simply negative 112.1 joule per mole Kelvin, okay, plus the molar entropy of Cu solid is just 33.150 joule per mole Kelvin, okay, minus the molar entropy for Zn sulfur will just simply be plus 41.63 joule per mole Kelvin, okay, plus the molar entropy for the second reactant, Cu2 plus, is just simply negative 99.6 joule per mole Kelvin. So that's basically it. Now we just do basic calculation. So the molar entropy of the reactant would just be negative 112.1 plus 33.150, which is just simply negative 78.95 joule per mole Kelvin, okay, minus plus 49.63, okay, plus minus 99.6 will just simply give you. So basically, I am working on this information, just this information here that I have put that stuff in, like I've put that red symbol on. So what I'm saying is positive 41.63 minus 99.6 will just simply give us negative 57.97 joule per mole Kelvin. So you have the change in standard entropy of reaction will be negative 78.95 joule per mole Kelvin, okay, plus 57.97 joule per mole Kelvin. So when you add this information up, the change in standard reaction entropy will simply be negative 20.98 joule per mole Kelvin. So this is basically the answer to this question. Now, our work is not done because the proper thing for you to do in chemistry is to go back to your question to make sure that you've put in the proper number of sig figs or decimal places in this question, because we're dealing with a bunch of additions. We're going to be working with just decimal places. So I have to look at each one of the information we have that we use in this particular question and determine the number of decimal places that is the lowest. And we're going to put our answer in the lowest number of decimal places. So in this place, we have one decimal place, okay? We have three decimal places. We have two here and we have one. So we're going to put our answer in one decimal place. So we're going to approximate to one decimal place. So that would be the change, standard entropy of reaction would be negative 21.0 joule per mole Kelvin. And this is simply the answer to our question. So yeah, if you have any questions so far, please put in the comment section. Now we're going to deal with the second reaction. The second reaction, rewriting it, is C, okay, 12H22O11 solid, okay, plus 12O2, okay, gas. Are you listening? Yep, you are. Would give us 12CO2 gas, okay, plus 11H2O liquid. This is a combustion reaction. So this is a combustion reaction of sucrose. This is actually sucrose. So yeah, I mean, we don't need that information to solve this question, but it's just a fun fact. This is sucrose. Anyways, so you have that, and remember, what did I teach you? The standard entropy of reaction is simply the summation of the molar entropy of the products, okay, minus the summation of the molar entropy of the reactants. I want to quickly mention something to you. You see this V value right here. This V value here is simply the coefficient, okay, of products, okay. I did not say it in the first one because the information was not necessary, but it's going to be very necessary in this one. While this one that I'm writing is a coefficient for reactants. You're going to see why this is important soon for reactants. So we have this formula. We're just going to start. So we're going to start with the product, right? The molar entropy of the product. We've got our first product to be 12 CO2 gas, okay, plus the molar entropy for the second product, which is 11H2O liquid, okay, minus the molar entropy for the reactant. We have the first reactant to be sucrose, so molar entropy of C12H22O11 solid. And make sure you put it all of this information in the proper phase, because the entropy, molar entropy for maybe H2O liquid will be very different from H2O gas, as well as going to be different from H2O solid. So the phase of each compound is very, very important. So that's why I keep saying solid, gas, liquid. It is for a purpose. It's very, very important because the values would differ based on the different phases. So we're going to do now the molar entropy for the second reactant, which is 12O2 gas. So that is it. So yeah, now we're going to rearrange this. So we have the molar entropy. We're going to rearrange this. We're going to say 12, which is the coefficient that I explained earlier, coefficient for products and coefficient for reactant. If the coefficient is not 1, you're going to do the second step. If the coefficient is 1, then we don't need to do the second step. That's why the first question we did on this video, we only arranged it once. We didn't do a second arrangement because the coefficient for every single molecule in this reaction is 1. Here we have coefficient of more than 1. So we're going to bring out the first coefficient. So that'll be 12 times the molar entropy of CO2 gas, okay, plus 11 times the molar entropy of the second product, so H2O liquid, minus, we're going to do the same thing here. This one, the coefficient is 1, so we're just going to rewrite this. So the molar entropy of C12H22O11 solid, okay, that's what we're doing here, okay, plus the 12, okay, times the molar entropy for the second reactant, which is just not 12. We brought out the 12 already. So that would be just the second reactant is just O2. So that would be O2 gas. Yeah, that's how it's done. So now we just simply substitute based on the information I told you guys at the beginning to pause. So the information from the resource section of our textbook. So we have 12, okay, times 213.74 joule per mole Kelvin, okay, plus 11 times Molar entropy of H2O, that would be 69.91 joule per mole Kelvin, okay, minus molar entropy of C12H22O11. So that's just going to be 360.2 joule per mole Kelvin plus 12 times 205.138 joule per mole Kelvin. So the molar entropy, sorry, the entropy of the standard entropy of reaction would be 12 times 213.74 is just simply 2564.88 joule per mole Kelvin, okay, plus 11 times 69.91, that's just going to be 769.01 joule per mole Kelvin. So this one's together, of course, then we got the minus. So that would be minus 360.2 joule per mole Kelvin plus 12 times 205.138 is just 2461.656 joule per mole Kelvin. So you're going to add up this information here as well as add up this information here. And we're going to input that information in our calculator. So the change in standard entropy of reaction becomes adding the first part, 2564.88 plus 769.01. That's just going to give you 3333.89 joule per mole Kelvin minus 360.2 plus 2461.656 joule per mole Kelvin. So that would be minus 2821.856 joule per mole Kelvin. The change in standard entropy of reaction will be 512.034 joule per mole Kelvin. So that is basically the answer to this question. Now, I wanted to also tell you this, right? When we're dealing with chemistry, remember we have to look at the proper number of decimal places since we have a lot of additions in this question. So we have the values we have. We have the molar entropy of reaction. We've got this in 2 decimal places, 1 decimal place, and then 3 decimal places. So we're going to put our answer in 1 decimal place. So our answer ends up becoming the change in standard entropy of reaction is 512.0 joule per mole Kelvin. And this is basically the answer to this question. If you have any questions, please put in the comment section. If you have any suggestions and concerns, also put in the comment section. If you're a student who is striving to succeed in all your STEM related courses and you would like a tutor, I'm a tutor for STEM related courses for students in middle school, high school, and college. And I do online tutoring for individuals as well as group tutoring. So if you need help, just make sure you don't forget to email me at shahabitutoring@gmail.com. And if you're also struggling and you're in need of any form of mentoring related to academia while you're trying to navigate your academic life, make sure you email me at shabitutoring@gmail.com. I also help students who are struggling to navigate the academic path to succeed. So I wish you guys all the very best. Assalamu alaikum wa rahmatullahi wa barakatuh.